Hello, welcome students. I am Rekha Thorat, Associate Professor. Today, I am going to discuss with you on next topic, mathematical induction of real analysis. Mathematical induction is a powerful method of proof which is frequently used to establish the validity of statements Pn for every natural number n. Mathematical induction is an important tool in proving the results in all branches of mathematics. Now, we consider the well ordering principle or well ordering property. The well ordering principle states that every non-empty subset of natural numbers n has a least element. If S is non-empty subset of n means set of natural numbers, then there exists small m belongs to n S such that m is less than or equal to k for all k belongs to S. That is, if S is any non-empty subset of natural numbers, then there exists small m belongs to S such that m is less than or equal to k for all k belongs to S. Now we consider principle of mathematical induction. Let S be non-empty subset of n such that first property is 1 belongs to S. Here S is any non-empty subset of n. Such that first property is 1 belongs to S. Second property is for every k belongs to n, if k belongs to S, then k plus 1 belongs to S. Then we have S equal to n. This is principle of mathematical induction. Now we consider first version of principle of mathematical induction. If Pn be any statement about n such that first property is Pn is true for n equal to 1, that is P1 is true, and second property is for k belongs to n, if Pk is true, then Pk plus 1 is also true. That means first version of principle of mathematical induction is if Pn is any statement about n such that Pn is true for n equal to 1, that is P1 is true, and second property for every k belongs to n, Pk is true, then Pk plus 1 is also true. That means if Pk statement is true, then Pk plus 1 statement is also true. Then this version is known as principle of mathematical induction. Then the statement Pn is true for all n belongs to n. Both the conditions here, small 1 and small 2, are essential to prove the validity of statements Pn. If one of the condition is not satisfied for some value of n, then the statement Pn will not be true for all n. That means here both the conditions must be satisfied for the statement Pn. If one of the condition is not satisfied, then the statement Pn will not be true. Statement Pn will be true if both the conditions are satisfied. Now consider the example. Let Pn is the statement such that n square equal to n. Put n equal to 1. Then P1 equal to P1 is the statement such that n square equal to n, put n equal to 1 so that we get 1 square equal to 1. That is 1 equal to 1 and it is true. Such that P1 is true here. Now we consider the statement Pk. We put n equal to k here and statement Pk is such that k square equal to k. But k square equal to k does not implies k plus 1 square. K plus 1 bracket square equal to k plus 1. But k square equal to k does not implies in bracket k plus 1 bracket complete square equal to k plus 1. Thus, here Pk is true, then Pk plus 1 is not true. That means condition 2 is not satisfied. Hence, Pn is not true for all n belongs to capital N, that is set of natural numbers. That means here the given statement Pn such that n square equal to n is not true for all n belongs to n. We have proved this example by mathematical induction. Here we prove that the statement is not true for all n belongs to n. Now we consider second version of principle of mathematical induction. Let small n belongs to capital N and let Pn be any statement for each natural number n greater than or equal to n naught such that first condition is Pn naught is true, second condition is for all k greater than or equal to n naught, the truth of Pk implies the truth of Pk plus 1. That means if Pk statement is true, then Pk plus 1 statement is also true. Then Pn is true for all n greater than or equal to n naught. Here the value n equal to n naught is called base value and the condition 2 is called the bridge. This is second version of principle of mathematical induction. That means for n belongs to capital N, let Pn be any statement for each natural number n greater than or equal to n naught such that first condition is Pn naught is true, second condition is for all k greater than or equal to n naught. If Pk is true, then Pk plus 1 is true, then Pn is true for all n greater than or equal to n naught. Here the value n equal to n naught is called base value and condition 2 is called the bridge. Now we consider principle of strong induction. Let S be the subset of n such that first condition is 1 belongs to S and second condition is for every k belongs to n if the set 1, 2, 3 up to k is less than or equal to S, then k plus 1 belongs to S. Then S equal to n. principle of strong induction states that if S is a subset of N such that 1 belongs to S, and for every K belongs to N, if the set 1, 2, 3 up to K is less than or equal to S, then K plus 1 belongs to S. Then S is equal to N if both the properties are satisfied. Thank you.